Welcome everyone to this live presentation, and in this live series that we do at 9 o'clock every single day, we look at what you need to know in order to be an embedded engineer. And I've broken it down to 13 different steps. First is marketing. We go to team building, learn about microcontrollers, toolchains, operating systems, schematic design, analog digital electronics, PCB layout, programming, mathematics, hardware design, testing, packaging, and sales CRM. So we don't just we don't just look at the electronic side of things, but there's so much more to it that really answers a lot of questions for you. For example, the first thing I put on my list is marketing, because it's really something that answers all the questions. Like, a lot of people ask, where do I get started? What do I need to learn? What career path should I take? What should I study at the university? Where should I start learning? And all of those things are answered to you through marketing, because it's the act of establishing communications, reaching out to different companies, looking what is needed, discovering different ideas. So it is through the communication, through the act of communicating, that people discover different ideas. Now, if you don't know what to do, if you don't know what to study, if you don't know where to begin, the chances are that you're not communicating enough, you're not communicating far enough, and you're not communicating often enough to figure it out. So, number one, learn marketing. Number two, team building. Like, find people that have complementary skills. For example, if you're an embedded engineer that does hardware, you need to find programmers. If you're a programmer, you can find other engineers that do hardware. And this is what we do in our community. So when you join our community, you find other people who are good at different things, and you can pair up and create projects together, because you can use each other's skills and you don't have to do everything yourself. But it's good to know for you what to do yourself as well. You learn microcontrollers. For example, this is a diagram of a timer, the timer 1 in an STM32 chip. Now, this timer is a very advanced peripheral that can be used for many different control tasks. And one of the things that it's very suitable for is, for example, 3-phase control of motors. And it is designed specifically for this task. So, for example, you have inputs here on the capture channels, and you have a special XOR gate that allows you to watch for changes on these inputs. And this XOR gate is actually used for reading Hall sensors for motors. Now, it has a positive output, a negative output, inverted output. So there's so much hardware already implemented on the chip to make it possible. Now, you need to know how to program it, of course, and that's what we do in our programming courses when we look at programming microcontrollers. Now, if you once you're signed up, you can get invited to live workshops. So, for example, today we have a live workshop where we're going to be doing C programming. Toolchains. One of the things that you can do with OpenOCD is a JTAG interface tool. So you can interface to the chip's JTAG hardware through a JTAG adapter. Like, for example, this one. This is an LPC Link 2 hardware, which is you can flash it with a standard firmware that makes it resemble a J-Link debugger. And you can then interface it with a lot of different tools. OpenOCD, JTAG stands for Joint Test Action Group. And one of the features of JTAG is that you can analyze pins on a chip. You can actually read out states of pins without having to go through software. So you can, for example, connect the chip through JTAG to your computer, and then you can look at the states of the pins. And the software can be running while you do that. But you can read out different types of information that is helpful for debugging the circuit board. You need to learn operating system design. We have two main operating systems today, which are targeting two classes of hardware. We have Zephyr for programming microcontrollers. It supports lots of different microcontrollers, but it's targeted at smaller devices. And we have Linux that is targeted at desktops and bigger devices and embedded systems that run Linux, that have some kind of ARM processor, that can run an environment like Ubuntu. Raspberry Pi runs Linux. Lots of systems that need to have complex connectivity. Linux really shines there because you have so many tools available, and you can use all the command line tools to transfer files, to do all kinds of things. You need to understand schematic design. So, for example, how many different transistors are there? Do you know what a P-channel MOSFET is? Do you know what an N-channel MOSFET is? Do you know when you should use which? Do you know how NPN transistors work? PNP transistors work? You need to be able to understand this. For example, do you know what the arrow means? Do you know that this is a P-channel MOSFET and this is an N-channel MOSFET? What is a depletion MOSFET versus an enhancement MOSFET? And one of the ways you can learn this is by looking at open source hardware. So there's so much hardware out there right now. You can literally like search for open source hardware, and you'll find a lot of schematics. And you can look at reference schematics as well provided by manufacturers. There's a lot of schematics provided with chips that show you how to implement a basic system with those chips that you can then build upon. But you can also look at the schematic and understand how it works. And number 7, you need to learn analog and digital electronics. So why and how do you place decoupling capacitors? Why do you need them? Why do you need to when do you need to have a coupling capacitor? So decoupling capacitor would filter out noise, and coupling capacitor would filter out DC currents. So it's going to let through frequencies, higher frequencies, but filter out DC currents. And you typically use coupling capacitors on input to amplifiers. For example, if you look at a schematic of an audio amplifier, you may see a coupling capacitor on the input to the amplifier. Why do you need pull-up, pull-down resistors? What is a high-Z state of a pin? What are push-pull, open-drain outputs? So when you're doing your schematic design, naturally, when you're doing your schematic design, you will go against these things, and you'll have to think about when you connect push-pull pins or open-drain pins. And also when you start programming your chip, many chips have configurable pins. So you need to be able to wire things together in such a way that you don't create electrical conflicts. So how do you connect multiple outputs together? Is it okay to connect them together, or do you need to have some kind of protection so that they don't get shorted? How do you do voltage level conversion? For example, when you're doing when you're interfacing 5-volt electronics to 3.3 volts controllers, you need to make sure that the voltage levels are converted to the lower voltage levels. PCB layout, also very important to learn when you're doing embedded systems. You start with the specifications. One of the ways you can do is you can start with specifications from the manufacturer, so that you don't create a PCB that cannot be manufactured by the manufacturer that you've chosen. How do you remember to make important components available on the PCB? For example, connectors, JTAG connectors. Is the PCB going to be mounted in a particular way where connectors are not going to be accessible easily because of other things that are mounted on top of it, for example? Do you need test points? Where do you place the test points to make them accessible? The difference between different solder methods, so that you can have enough space between components so that they don't get shorted when they're soldered. Then you get into programming, and in programming you start dealing with things like memory management. What kind of allocator should be using? For example, FreeRTOS has different allocators that you can use for different things, and more complex RTOS environments have also different allocators. Do you even need to use an allocator? Should you use who owns the variable that you allocate? Like, who should be deallocating that variable? Should you have a subsystem that allocates and then deallocates the variable, or should you return an allocated variable and something else deallocates the variable? Should you allocate memory in blocks and then partition it into smaller objects and then delete the whole block? Or should you allocate it in smaller objects and then delete each object by itself? When should you use which? So depending on how you're going to be using your memory, depending on the patterns of allocation, maybe one is better than the other. But in a different time, a different strategy might be more efficient than allocating a single block. And when you do programming, you then get into mathematics. Like when you start doing motor control, you get into, for example, you need to understand Park and Clark transforms in order to work with three-phase currents. You need to understand calculus in order to work with differential equations. And you need to understand things like Laplace transform in order to transform differential equations into a domain, into frequency domain, where the solutions are basically solutions to polynomials. So it becomes a lot easier to find the solutions when you make this transformation that transforms your equations into a ratio of polynomials, which we call the transfer function. Hardware design. This is really interesting topic. So for example, how does a processor work? How do you really understand how a processor works? Well, one way is you create your own processor. And there's really good examples of this. One example that you can look at, which is completely open source, is Verilog Boy. It's a Game Boy, it's actually Game Boy hardware implemented in Verilog. And because it's implemented in Verilog and compiles under Icarus Verilog, Icarus Verilog also has a tool called Verilator that compiles the Verilog into a simulation. And you can then actually run the simulation, and you can feed it with binary code that then runs on the simulation, and the simulation then produces an image of the screen of the Game Boy. So you can really start learning how CPUs work, and it's quite simple CPU. It's not that much code. It's easy to understand, and you can actually start experimenting with it and do so completely in software. You don't actually need to flash this to an FPGA in order to be able to test it, which is really cool. So you can make changes. You can make a little change in the CPU, then run your software, maybe compile a new software. So the way this one works is that it has an assembler, a special assembler that is used for Game Boy, that is designed to compile software for Game Boy, and it's also open source. So you can use that to create an assembly program for your own CPU that you're experimenting with, and then add your own peripherals to it, and then try to use those peripherals from the assembly program. So it's a really interesting way to understand how things work at the lowest levels. And when you do firmware development, when you do embedded engineering, you're going to find yourself in the FPGA world. You're going to find yourself dealing a lot with hardware. So learn this. This is really useful. Documentation and testing. Should you have like online tutorials for software that is easily accessible, where customers can go in and read how to use the software? Should it be open source or not? Like, what licensing should you be using? Benefits and drawbacks of open source. Sometimes it's beneficial to do open source. Sometimes it's not. It depends on what type of product it is. You're also going to be dealing a lot with sales. Like, you always have some sort of sale going on, so you have to understand that it doesn't matter if you're an embedded engineer. You're going to have to learn sales anyway. You're going to learn. You're going to have to understand how you take this process from start to finish. Do you need to find distributors for your products? Do you need to sell directly to consumers? There's been different models of doing this, and many people lump together marketing and sales, but marketing is something you do in the beginning. Like, marketing is something you should really start when you're born, right? It's really important that children get children when they're born, everybody goes like, "Oh, so sweet little baby," and everybody is. And the child is basically marketing without even understanding it. But then something happens, and the child goes to school, and and you never talk about those things. Like, you never talk about marketing. But really, it's something that you should be like doing from the very beginning, because it opens up for ideas. Like, you get new ideas because you're communicating with other people, and so it's easier to get answers to the questions that you might be asking yourself. So this is it for today, and I'm doing this live sessions every single day at 9 o'clock. You can also go to switchbetter.com/free and register, because once you register, I can send you an invitation to the next workshop. So for example, today we're doing an in-depth workshop on embedded C. We're going to go into detail on programming in C and go through examples. You can bring your code as well. You can I can go over your code with you on the live workshop, and that's kind of how it works, right? So go to switchbetter.com/free, register there, and I'll talk to you later.